Morning students, in the previous session we have studied the design procedure of flange coupling. Now in this session we will take the numerical problem on flange coupling. Let us have problem. In rigid flange coupling, to transmit 20 kilowatt at 700 rpm, the flanges are of cast iron and other parts of C40 steel. Assume stresses for cast iron. Tensile stresses equal to 28 Newton per mm square. Compressive stresses equal to 60 Newton per mm square. Shear stresses equal to 10 Newton per mm square. And stresses for C40 steel, tensile stresses equal to compressive stresses equal to 100 Newton per mm square, shear stresses equal to 40 Newton per mm square, bearing stresses or crushing stresses equal to 125 Newton per mm square. Determine the dimensions of the shaft, key and flange if the number of bolts are 6. First of all, we write down the given data. Power P is equal to 20 kilowatt, that is equal to 20 into 10 raised to 3 watt. In RPM, 700 RPM. For C40 means tau shaft equal to 40 Newton per mm square, sigma T is equal to sigma C is equal to 100 Newton per mm square, sigma crushing is equal to 125 Newton per mm square, and for cast iron tau Ci equal to 10 Newton per mm square, sigma T is equal to 28 Newton per mm square, sigma C is equal to 60 Newton per mm square, and number of bolts is equal to 6. This is the given data. In order to draw the figure of flange coupling, we will draw this type of structure. About the center line, we will draw the parallel lines at a distance D, then 2D, then 3D and 4D, and vertical lines at a distance 0.5D, 0.5D, and this distance should be 1.5D and this should be 1.5D, because this is the shaft and this hub is double 2D, where D is the diameter of the shaft, and this pitch circle diameter of the nut is 3D and outer diameter is 4D. Hence we will draw the parallel lines at a distance D, 2D, 3D and 4D, and vertical, and this distance, this is 0.5, this is 0.5 and this is 1.5. This distance is 1.5. So we will take this distance as 0.5D and this distance as 1.5D. Now with the help of parallel lines, we will complete the figure of flange coupling. Now this is the figure of flange coupling, showing the half sectional view of flange coupling. The keys are at 90 degrees. These are the bolts, and this is the hub, and these are the flanges, and this is the shaft. Now this is the model of flange coupling. These are bearings, and this is the shaft, and these are the bolts. Now we will open the bolts by removing the nuts. Now in this way, this is the details of the flange coupling. This is the shaft with key, and these are the flanges. Here holes are there where bolts are inserted. This is the hub, and this is the outer diameter of the flange. Shaft double the diameter is hub, 3 times diameter is the pitch circle, diameter of the bolt, and outer diameter of the flange is 4d. Now procedure. First we calculate the torque by the formula power is equal to omega t. Omega is equal to 2 pi n upon 60 into now putting the value of omega 2 pi n upon 60, and this formula becomes P is equal to 2 pi n upon 60 into T. Now T is equal to 60 into P upon 2 pi n. Putting the value of power and N, we will get torque is equal to 272.84 Newton meter. We will convert this into Newton millimeter by multiplying 10 raised to 3. So torque is equal to 272.84 into 10 raised to 3 Newton millimeter. Now after finding the value of torque, we will find the diameter of shaft. This is step 1, considering in pure torsion. From the formula torque is equal to pi by 16 tau d cube. Putting the value of torque and permissible shear stress, we will find the diameter. That comes out to be 32.63 millimeter. Say we will take 33 millimeter. Now from empirical relation, capital D is equal to 2d, that comes out to be 66 millimeter. D1 pitch circle diameter, that comes out to be 99 millimeter. D2, that is outer diameter, equal to 4d, that comes out to be 132 millimeter. L is equal to 1.5d, that comes out to be 49.5 millimeter. We will take 52 millimeter. TF is equal to 0.5 into d, that comes out to be 16.5 millimeter. Width of the key, that comes out to be 8.25. We will take 8.5 millimeter. Thickness of key, that comes out to be 5.5 millimeter, and length of the key is equal to length of the hub, that is equal to 52 millimeter. Checking the dimensions of hub for torsional shear stress considering hollow shaft. From the formula T is equal to pi by 16 tau induced into capital D cube in the bracket 1 minus k raised to 4, where k is the ratio of shaft diameter to hub diameter, that is k is equal to 0.5. Putting the values of torque, outer diameter of hub and k, tau induced comes out to be 5.15 Newton per mm square, which is lesser than the tau cast iron permissible. The value of tau cast iron permissible is 10 Newton per mm square. Hence hub is safe for torsional shear stress. Checking the flange for torsional shear stress. Force is equal to shear area into torsional stress. Now this figure shows the shear failure of the flange, and the shear resisting area is given by this shaded strip, and the area of this shaded strip is equal to pi d, that is the circumference of the strip or hub, and into thickness of the flange, that is equal to Tf. So resisting shear area is given by pi d into Tf. Now the shear force is given by shear area into torsional stresses, where F is the shear force. F is given by pi d into Tf. This is the shear area into tau induced. Now torque is equal to force into radius. Putting the value of force, pi d into Tf into tau induced. Now the formula becomes torque is equal to force into radius. Radius is equal to d, capital D by 2. Now putting the values of the torque, outer diameter of hub, Tf and pi, tau Ci induced comes out to be 2.41 Newton millimeter square, whose value is lesser than tau permissible, that is equal to 10 Newton per mm square. Hence flanges are safe in shear. Checking the dimensions of key for shear. From the formula T is equal to WL into tau induced into D by 2. From this we will calculate tau induced, that comes out to be 38.7 Newton per mm square. As the value of tau induced is lesser than tau permissible, that is equal to 40 Newton per mm square. Hence the dimensions are safe for shear. Now checking the key for crushing. From the formula, T is equal to L into T by 2 into sigma Ck induced into D by 2. Now putting the values of torque, length, T and diameter of the shaft, the sigma Ck induced comes out to be 115.63 Newton per mm square, which is lesser than the sigma permissible, that is given 125 Newton per mm square. Hence dimensions of the key are safe for crushing. Is determination of dimensions of bolts. Considering the failure in direct shear, load on each bolt is equal to pi by 4 dc square into tau b, and the total load on the bolt, that is equal to load on each bolt multiplied by number of bolts, that is equal to n in the bracket pi by 4 dc square into tb. Now torque is equal to total load on the bolts multiplied by radius. Putting the values of total load on the bolts and radius, that is d1 by 2, and torque, we will have the value dc is equal to 5.4 millimeter. Now from empirical relation, do is equal to dc upon 0.84, we will calculate the outer diameter of the bolt, that comes out to be 6.428 millimeter. So we will take 10 millimeter. So we will take the bolts of 6 bolts of M10. Thank you very much. This is all about the design of flange coupling. We will meet in next session.